Hi, everyone. Welcome to the Data Scientist Podcast. I'm very happy to have here with us today Tom Burns, a PhD researcher in Okinawa, Japan, who's working in the area of neural networks and computational neuroscience. Hi, Tom.
Hi.
Would you like maybe to introduce yourself and tell us a few things about your work? You're probably going to do a better job at it than what I'm going to do.
Sure, yeah. So I'm originally from Australia, and I currently am a PhD student in Okinawa, Japan, as you just said. And I'm interested in how the brain is basically so intelligent. And in particular, I'm interested in how neural networks can do all the things that they do, both in biological neural networks and artificial neural networks. And I'm quite interested in memory and navigation, as well as how we can use geometry and topology and ideas from mathematics to improve those sorts of tasks or understand those sorts of tasks in neural networks.
That's fascinating. So those of you who are regular listeners to our podcast or regular viewers, for those of you who follow us on YouTube, you'll know that most of our episodes are around things like data strategy, etc. But as you might have just realized, this episode is going to be a bit more theoretical. Computational neuroscience and general AI and these kind of areas are really passions of mine. So I'm very happy to have the opportunity to speak with Tom today about these topics, who's a researcher in this area. And that being said, I'd like to ask you, Tom, a few things about your work. I know you're working on Hopfield networks and attractors. That's something very interesting because that's an area of research that has been going on for decades. I know a few decades ago, which was before deep learning really took off, or maybe before even deep learning was discovered, there were some researchers tried to use this kind of networks for different applications, but things didn't really work out. What do you feel is different now compared to 20, 30, 40 years ago when these types of neural networks were discovered, both in AI and applications, but maybe also in cognitive science, and how we approach now these types of networks and models?
Yeah, well, that's a very big question. And as you know, back in the 80s, basically, John Hopfield created this model, which we now call the Hopfield model. And it was an associative memory network where each of the neurons took on binary values, plus or minus one, or you can use 1 and 0. And you have some number of these neurons. Let's say you have 100. And then what you do is you store memories in this network as sort of binary activations of the neurons, 1 or 0 or plus or minus 1. And if you do that in a random fashion, it turns out that theoretically you can store about 14 patterns if you have 100 neurons, until when you add, say, the 15th or 16th pattern, then you can't sort of pattern match the patterns. That means you can't recall the patterns. If you give part of the pattern in this network, then you can sort of retrieve the whole network. And for a long time, that was sort of thought of as sort of a theoretical concept about how to store and retrieve memories in not only maybe neural systems in general, like biological neural networks, but also with some applications. These applications are very limited, as you said. First of all, it's limited in the data structure, right? You can only use these binary values. But second of all, it's quite limited in terms of what you can store in the number of items of memory that you can store and how you retrieve them and how these things are used. For a long time, it was like that. And people did different extensions, different types of technical work. Theoretical people, especially physicists, did a lot of work on finding out these theoretical capacities because they turn out to have a correspondence to different physical systems to do with magnets and atoms and things like this. Specifically, if your viewers are interested, they can look up spin glass systems. But what happened more recently in the last decade, and especially in the last 5 years, is that we started to realize that actually you can have, well, it was discovered a long time ago as well, back in the sort of the 90s, I think, that you can, instead of having binary values, you can extend this to continuous values between, let's say, 0 and 1. But then this had some technical problems. But then the last 5 years, we've realized, actually, no, we can overcome that. We can store even more patterns, and we can store these continuous valued patterns. And maybe without going into all the technical details, because it's a long technical story, but it turns out that transformers and the attention mechanism used in transformers in modern neural networks is actually doing something basically equivalent to the Hopfield network update rule, which is how the Hopfield network starts to retrieve a memory and continually retrieves a memory. So it's doing an associative memory recall task. And what's interesting in particular about transformers is that it came from a totally different, line of research, and it turns out to be basically just serendipitously falling on the same sort of intuition and cognitive or computational structure as Hopfield created back in 1982.
That's fascinating. And if my memory serves me well, the Hopfield network is a recurrent neural network, right?
Yes, that's right. Yeah.
Whereas the transformer is based on convolutions, which are essentially more of a feed-forward model. And I remember there was lots of fascination around recurrent neural networks because I guess some might say that they have, in some ways, let's say, infinite capacity because of this way they work. But how do you find recurrent neural networks in research and applications these days? Because I feel that while they're quite powerful, I think they've been overshadowed by convolutions. Like, you just gave this example, I guess, because from a computational perspective, they're just easier to handle. I don't know what you're saying in this area.
Yeah, I think that's exactly right. It still appears that way to me. Granted, we are the ones that make the computers, right, and the architectures which make one of these structures more efficient than the other. And I think that it's an open question as to which one is better. No doubt, our brain is a recurrent neural network. However, that doesn't mean that we have to model everything off the brain. The classic example of an aeroplane and a bird, and the engineering trope that's associated with that. But my opinion actually is that we don't necessarily have to use a recurrent neural network to use ideas developed over many decades in Hopfield networks, because in theory, the idea of transformers is to apply sort of one step of a recurrent update and just treat the vector length, or your neurons in one layer, instead of doing a convolution, do something like a convolution and just have the same length vector as the next step. And you could sort of theoretically think of those neurons as identified in terms of theoretically analyzing it from the recurrent neural network perspective, which is not intuitive or physical, I take it, in the feed-forward or convolution perspective. But if you grant that, then from there you can, I think, do everything. You can do everything theoretically as you did before in the current networks.
Okay, and so what are the benefits of studying Hopfield networks and attractors these days in the current state of neural networks and the cognitive science?
Well, transformers themselves have already been proven hugely effective. And the question is why, I guess. Why are they so effective, and how? And how, in particular, could they be even more effective, given that we see that certain particular modifications to the transformers for different modalities or different tasks can improve their performance. But the question is why? And there are intuitions and sort of heuristics that people use here, and there is some developing theory. But I think, given that we have now this treasure trove, this secret tunnel back to an amazing wilderness, which is now looking a bit dusty on the shelves. The Hopfield network papers, decades old, a lot of them. But given we have this connection, I think that we should try to exploit it, and we should try to look back and see, what are those old papers doing? What are those old ideas doing? And can we recast or reinterpret some of those old ideas into transformers, because they were very general, very theoretical, most of them, and there's already basically a wealth of data back or knowledge back there that we can still use today. But it requires some math, so I'm not necessarily going to go into all the details of that in particular, but I can speak of a couple of examples if you're interested.
That's interesting. What I wanted to ask you next is around general artificial intelligence. What's like your feeling about this? Obviously, everyone has an opinion. no knows
Yeah.
the truth. So do you envision that maybe some of the work that you're doing in computational neuroscience is going to eventually lead to general AI, like recurrent neural networks, or maybe some of the old networks like revisited with more computational resources? Or do you think that maybe we'll do something like general AI, just simply using the current deep learning architectures, but just making them bigger and bigger? I know that DeepMind, they are creating this very big network which tries to do multiple tasks in one go, like label pictures, I don't know, generate stuff, understand language, all that.
Hmm.
So what's like your intuition about this, and what other researchers are saying in this area?
I think a lot of people, at least in my neck of the woods, will say no. There's not enough there yet to make general AI. However, I don't think that we even have a good definition or agreement on these terms and what qualifies or not. So that itself is problematic, and I think will lead some people to claim that we already have that, or we already have, sentient AI or something, and we may well have under some definition. So I think it's maybe more of a philosophical question, and I think an unsettled one for now. But at the very least, I would like to see more sort of cognitive science, computational neuroscience, and even other forms of mathematics in AI. And I think that will actually be very useful if we do that.
Yeah, actually, if we look, let's say, 50 years back into the past, then we'll see that cognitive science was more integrated with AI and linguistics. And now it seems that things are segmented so much that some researchers might be saying, "Oh, I'm only doing deep learning." They might not even say machine learning anymore. Do you think that in the search for general AI, we might observe a reintegration of different fields or in cognitive science?
I think we have to. And I mean, uh, just as one example, Jan LeCun had a white paper, I think earlier this year, that basically, was advocating for this sort of thing. And he's not alone in that, and he's certainly not the first to do so. But he's a big figure in the space, and I think that was great that he sort of acknowledged that. But I think Hinton, Bengio, all the big players are sort of hinting at and have for a long time been sort of saying we should try to reunite things a bit more. Unfortunately, there's a bit of a cultural issue or misunderstanding, I think, sometimes between these different fields, and people ultimately care about different things as well. If you're an engineer that cares about sort of outcomes and products, compared to if you're a scientist and you just care about the nature of things, those are totally different paths that people might be interested in pursuing, or outcomes that people are measuring. So I think there are some cultural problems that we'll encounter, and I think if we can overcome them, then we'll enjoy the fruits of all of our different expertise and all of our different resources.
Yeah, I think maybe part of the problem in this case is that AI has been commercialized to a large extent. So I guess a large part of the money for research and development is coming from big tech, and they're primarily interested in applications. So I guess when I remember, for example, reading about DeepMind last year or 2 years ago, and there was this criticism that they hadn't produced enough value for Google. They were too academic. And I guess you're always going to have this kind of tension. So if you say, "Oh, I'm a cognitive scientist," you do know that whatever it is you're working on, it's probably not going to have an immediate application, right? The applications
Yeah,
might come later down the line.
yeah, exactly. And I mean, I think the easiest example I can think of in this general theme is that um, we use vector spaces
Mhm.
basically everywhere in machine learning. Why? Well, I guess because the computer structures that we have set up and commercialized and are abundant are those that which rely on those linear sort of algebraic structures, and that's okay. But there are other structures, there are other kind of things out there, and certainly, I think, yeah, if we ponder on what is a computer, what is intelligence, long enough, we realize that it's not linked at all. It's not obvious at all that we should rely on all the different structures that we have in our current sort of arsenal. And that's actually quite a limited subset or a limited set of definitions about what intelligence is and what a machine can do or be.
Yeah, that's a very interesting point. And the risk of getting a bit technical, if we weren't using vectors, what other data structures do you think we could use in order to represent knowledge and computation?
I mean, an obvious area and one which is already being explored are graphs. And these are, where we have vertices and edges, or people call these networks as well, with like nodes and connections between the nodes. The classical example for anyone that doesn't know what such a structure looks like is a social network where the people are the nodes or vertices, and then the edges are like the social connections between people, like in Facebook or something, or Twitter. But you can even have like high dimensional generalizations of that. You can have complexes, for example. And these are, these are starting to get away from geometry, and you go down to like a topological structure. After that, you can even go down to just an algebraic structure. I think, for example, structures like, there was a recent paper on cellular sheaves. This is the idea of attaching different objects like above the vertices and edges. That was recently done for a neural network, but still they were just attaching vector spaces above these things, so it wasn't particularly interesting. Yeah, I think basically there are many more structures out there which are interesting and which could be useful.
Yeah, that's a good point. I remember many years ago when I was studying cognitive science, there was this course talking about knowledge representation, and it was essentially talking about different mathematical models of representing knowledge within cognitive science. And it looks like everything's dominated by vector spaces, but there are like other ways to represent knowledge. And going back to your example about the airplane and the bird, like there's this, for those of you who don't know about it, there's this argument that just because we know that birds can fly doesn't mean that creating a flying machine means that you have to imitate birds 100%, right? Because we don't. So it's the same with general AI. Just because we know that the brain is intelligent doesn't mean that we have to imitate it 100% to create intelligence. Going back to this example, we don't know which would be the best data structures for intelligence, I guess. And some of the things like around vectors and tensors and all that, they were a bit accidental, as in neural networks ended up being very effective, and then someone realized, oh, I can use a GPU for that, because GPUs are essentially optimized for linear algebra, and one thing leads to another. Which was, I guess, a bit unintentional. NVIDIA never intended to get into AI, and no one would have imagined maybe 30 years ago that tensors would be so popular in this type of computational machine.
Yeah, exactly. And I personally think things like lattices could be extremely useful. Yeah, I mean, there are so many different types of structures out there, basically, and people are unfortunately sort of stuck in what works. No doubt it works, and so maybe that's a reason to stick with it. But I wonder what would history be like if we had have just happened upon a different sort of data structure that, or, if NVIDIA, to make computer games and whatever else they optimized for, whether or not a different set of mathematics would have been our basis that we're now using.
Yeah. I completely agree. So I guess only time will tell. So before we go, if you could make a prediction for the next, let's say, 5 to 10 years, what do you think is going to really stand out in the world of AI and neural networks and cognitive science? If you could say, for example, one thing.
I think it's kind of in the theme of what we've been discussing. I think people will come to realize that there are deeper connections between these structures, and that there can be sort of usefulness going in both directions to understand the brain and to understand and create better AI. And that in that process, we'll probably discover some new structures and techniques which are not currently mainstream, I think, in either field.
Yeah, sounds good. I guess my prediction would probably be something along the same lines. I wouldn't be as bold as saying, oh, we're going to have a general AI in 5 years or something. I don't think that's going to happen. We're definitely going to have, experience some incremental progress, maybe some integration of different fields, which is definitely a good thing. It's definitely a good thing. It will probably get us closer to understanding the human mind, and also what intelligence really is, and how we can actually create more intelligent machines than the ones we currently have. So yeah, I think our time's up. But thank you, Tom. It was
Okay,
a very
sure.
interesting
No
discussion.
problem. Yeah, thank you. Thanks very much.
Thanks everyone for staying here with us today. We hope to see you again in some other of our podcasts. And make sure to check out the datascientist.com for more content about AI, data science, and blockchain. And before I go, a couple of notes. If any of you are interested in pursuing a career in data science, make sure to go to the datascientist.com and drop me a message. I'll be very happy to help you out because we're starting a new program for aspiring data scientists. And also, if any of you are an entrepreneur, a CEO, a manager, and you need some help with data science in your organization, I'm more than happy to help you out. We have a network of partners specializing in different areas of applied data science and related fields. So just make sure to get in touch. So thanks, everyone, and hope to see you soon. Thank you.